Today we'll be talking about one of the most important aspects and topics in both deep learning as well as machine learning. So this comes under the second unit of the deep learning course, and it is regularization. Regularization. So let me take you through the necessity of regularization. We know that in machine learning, one of the problem or is the phenomena called overfitting. It is a phenomena which has to be avoided. So technically speaking, a model performing accurately on training data, but very poorly on test data or unseen data. This phenomena is known as overfitting. So on training data, your model is performing with 100% accuracy or maximum accuracy. But the same model, when you test it with different data, it is performing very poorly. Let me give you an example. Suppose you are in engineering, you have internal examinations, or we call it as mid examinations. So generally students will get prepared for some important questions, and if those questions come in the mid examination, the student may get 40 out of 40 uh, in internal examination. That means in on training data you are 100% accurate. But the same student, when he writes semester end examination or external examination, if he studies only those mid questions, he will certainly fail or his performance will come down. So this is known as overfitting. That means your model is too much adapted to the training data. Even a small change in training data or data, your model cannot perform well. Let us try to understand this on a graph. For example, this is a two-dimensional data, and you have your data points here. Let us say this is training data, and this training data is fit. Our model is fitting this training data absolutely better, no deviation at all. So it is performing, your model is performing absolutely on wonderfully on training data. But the same model, when you test it on the test data, for example, the test data samples are here. Now your training, our model is performing very well on training data. But when the test data appears, the performance is uh, decreased or it is very poor. So to avoid this overfitting case, we adapt some strategies. In the previous courses, you might have known about validation data. If I come back to my example of internal and external, to avoid this poor performance in external examinations, in between, some, of course, not in engineering, but in intermediate, what they do is they conduct a pre-final exam. So that is something like a preparation for the final. So this we call as validation data. So when 100 samples are given, generally we keep 70 or 80 for training, and the remaining 30 for testing. So to avoid overfitting, what we want to do is, let us keep 70 for training, then 15 for validation, then 15 for testing. So our intention here is we want to expose our model to robust changes in the data. We don't want them to adapt. For example, if you think about tables, kids will be by hearting 2 ones are 2, 2 threes are 2 twos are 4, and so on, and 2 tens are 20. Suppose if you ask somewhere to what is 2 eights are, because they have been habituated to read the whole table, they will start from 2 ones are 2 and they will come there at 216. That means they have habituated to one type of data. So that's why some people, what they do, they will make the students to read the tables from bottom to the top, or some random like 2 twos are 4, 3 twos are 6, 4 twos are 8, something like that. So we want our model to adapt to different changes in the uh, data. This is known as overfitting. And to avoid overfitting, one of the strategy is validation data, and another one is cross-fold. Suppose you have 10 samples, and out of 10 samples, you are using 8 for training and 2 for testing. So first time when you train with 1 to 8. Then use the 9 and 10 for testing. Second time when you train it from 2 to 9 and use 1 and 10 for testing. Third time, 3 to 10 and use 1, 2 for testing. Next 4 to 10 and then 1 and use that remaining 2 and 3. So this is known as cross-folding. Even when we talk about bagging or boosting, what are they? This overfitting is a problem in almost all the machine learning and deep learning techniques, but especially when we come to decision trees, this is a very, very big problem. That's why what we have done, a big decision tree is broken into small trees, that is known as ensemble learning. Ensembles. We make small trees, and those weak trees will train them. And when we have small trees of n number of trees, certainly their performance will be more. And what is bagging? Bagging is bootstrap aggregating. Bootstrap aggregating. What we do? We prepare a sample, random samples. For example, you have 10 samples and you want to prepare 10 samples. First, what we will do? We will keep 1 to 8 and 9 two times. This is sampling with replacement. Then you may have 2 to 8 or 2 to 9, and then 7 maybe twice or thrice. That means we want our model to look into diversified data rather than seeing only one data. So this is one way. And apart from this, another solution is regularization. Regularization. Here, uh, this is a topic where we use norm penalties. First of all, let us try to understand what is norm, what is L1 norm, and what is L2 norm. Then we'll understand how those norms can be used for regularization. So we know that whenever you have any uh, two-dimensional points, let us say this is our two-dimensional space, and you have 2 points. This is x1, y1, and another point x2, and both are, let us say, these are vectors, and the resultant vector you can calculate from the resultant vector can be calculated from the magnitude can be calculated from square root of y2 minus y1 whole square plus x2 minus x1 whole square. What you are doing? This is your y2 minus y1, and this is your x2 minus x1, and the resultant magnitude is y2 minus y1 whole square plus x2 minus x1 whole square. Of course, this we call as Euclidean distance. So here we are calculating the resultant with the squared terms. Squared. Another way of calculating a resultant vector is, instead of squares, let us take the absolute value, y2 minus y1 plus x2 minus x1. This is known as Manhattan distance. All these things you know already, right? You know it. Now, this way of using squared terms for the resultant vector is known as L2. Now, when we use, instead of square terms, when we use absolute term, we call that L1 now. So remember this simple difference in the beginning, though there are many differences, but before we go into that regularization, let us understand the fundamental difference between these two norms. L2 norm deals with squared terms, L1 norm deals with absolute terms. Now, when we see this terminology, even in regularization, we have these two regularizations, L2 regularization, which is also called ridge regression, which is also called techno regulation. Whereas L1 regularization is also known as lasso, least absolute solution, shrinkage solution operator. So lasso regularization. So when we are dealing with squared terms, that means here we'll be adding a squared penalty. We'll be adding a penalty to the function, objective function. This is squared penalty and this is not squared, absolute penalty. Now what we are doing here, this overfitting is occurring because of the phenomena of high variance and low bias. High variance. That means your model is very sensitive to any changes in the input. What is when you make changes in the weight, it is responding very abruptly. That we call as high variance. And you know the trade-off between the variance and bias. If you reduce the bias, variance will increase. And if you reduce the variance, bias will increase. So these are opposite to each other. This is, so if this is bias, high bias will lead to low variance and high variance. So if you want to reduce the bias, variance will increase. If you want to reduce the variance, bias will increase. So remember this very, very important point. The overfitting is a phenomena where your model shows high variance and low bias. What we mean by variance? Sensitivity to the changes in the input. High sensitivity. Even if you change a small value, your model will not perform well. High variance, low bias. This is overfitting. Similarly, what is underfitting? Underfitting, low variance and high bias. If your bias is very high, your model will underfit the data. It will not fit even the test data properly. And obviously, high bias and high variance is totally undesirable situation. What we need is low variance and low bias, but that is not absolutely possible. So remember these points, very, very fundamental point, overfitting and underfitting. And to avoid overfitting, what we are doing is, because our weights are very sensitive, we are penalizing, we are imposing a fine penalty on the changes that we make. That means the weights. Of course, the parameters that we have are weights and bias. And we are not touching the bias in regularization. We are adding penalty, imposing penalty to the weight. If it is L2 regularization, we will add squared penalty. If it is L1 regularization, we will add general value, not a squared one. So regularization is a phenomena where we want to avoid overfitting by adding penalty to the cost function or objective function. So we'll continue this discussion in the next lecture.